In the previous segment, we delved into the origins and acceptance of the Big Bang theory, clarifying that the term Big Bang should be understood as a rapid expansion of space rather than a traditional explosion. The entire universe, in a finite amount of time, evolved from an extremely dense and hot initial state. Furthermore, while the Big Bang theory is widely accepted, there are other scientific explanations for why the Big Bang occurred and what preceded it. However, these explanations fall beyond the scope of the Big Bang theory itself and involve separate theories. For the purpose of this series, we are focusing on the widely accepted Big Bang theory to provide an overall understanding of the universe's history. Later on, we can explore more speculative theories. Today, let's focus on the first second of the universe's existence when the Big Bang began. In this incredibly brief span of time, the universe underwent astonishing processes. It's important to note that traditional Big Bang models do not encompass many details of the universe's early moments. Many of the questions that these models couldn't answer were addressed by combining quantum mechanics and introducing inflation theory. As we approach the singularity at the instant of the Big Bang, t equals 0, the speculative elements in our theories tend to increase. So, some of the finer details need not be overly concerning. Are you ready? The Big Bang is about to begin. The earliest moment of the universe, referred to as the Big Bang singularity, is obtained by time reversing the universe's expansion using the principles of general relativity, which also serves as a prediction of the theory. However, at this moment, all the mass in the universe is concentrated into an infinitely small point, implying infinite density and temperature. Space and time are indistinguishable at this instant. The existence of the singularity renders general relativity inapplicable. In fact, not only general relativity, but all known scientific theories fail at this singularity. General relativity primarily explains macroscopic behavior on large scales, while at the quantum level, matter exhibits fundamentally different properties requiring quantum mechanics for explanation. Quantum mechanics does not encompass gravity, so a new theory is needed to explain such large yet small scenarios as the singularity. Some theorists propose that once we solve the problem of quantizing gravity and achieve a unified theory of everything that encompasses all four fundamental forces, the need for the singularity hypothesis might diminish, potentially revealing the true nature of the universe before the Big Bang. Following the singularity at t equals 0, there is a period from 0 to 10 to the power of minus 43 seconds known as the Planck era. This era derives its name from the Planck time, which is the smallest unit of time in quantum mechanics, approximately 5.391 times 10 to the minus 44 seconds. This value is based on three constants: the Planck constant, h, the gravitational constant, g, and the speed of light, c. The Planck time defines the distance a photon travels within a Planck time, which is termed the Planck length. During the Planck era, the universe's radius is roughly the size of a Planck length. However, during this period, photons haven't yet formed. This is a theoretical assumption. Given the minuscule scale of the universe during the Planck era, the quantum effects of gravity are pronounced, making gravity significantly weaker compared to the other fundamental forces. All the fundamental forces are unified into a single force known as the superforce. Because the descriptions of gravity in general relativity and the other three fundamental forces in quantum mechanics haven't been effectively integrated yet, predictions on scales smaller than the Planck time remain elusive. Therefore, our understanding of this phase of the universe is quite limited. After the Planck era, there is a brief grand unification era. Here, grand unification refers to the convergence of the strong, weak, and electromagnetic forces, excluding gravity. At the end of the Planck era, the universe undergoes a phase transition, and gravity separates from the superforce, becoming an independent entity. For the strong, weak, and electromagnetic forces to unify, a prediction based on quantum mechanics was made, and the fundamental particles carrying these forces have already been discovered in experiments. Scientists have used particle accelerators to create environments akin to the early universe's extreme temperatures, albeit on a much smaller scale than the actual Big Bang. From these experiments, evidence of virtual particles that carry these forces has been observed. Apart from photons carrying electromagnetic force, other particles like gluons, which carry the strong force, and W and Z bosons, which carry the weak force, were identified. According to the grand unification theory, these forces might be different facets of the superforce that unify at extremely high temperatures. As the temperature decreases, they would manifest as the distinct strong, weak, and electromagnetic forces. The phase transition in the grand unification era leads to the separation of gravity, transforming the superforce into the grand unified force. Following this, there is a second phase transition where the strong force separates from the grand unified force, leaving behind the electroweak force, a combination of the weak and electromagnetic forces. This transition might have given rise to something crucial, a massive, nearly invisible particle that only interacts weakly with normal matter, what we call dark matter. Additionally, during this transition, the phenomenon of cosmic inflation occurs. After the grand unification era, the universe experiences an exponential and extremely rapid expansion. In just about 10 to the power of minus 33 seconds, the universe expands by a factor of 10 to the power of 26, and the temperature drops to 100,000th of its previous value. The theory of cosmic inflation was first proposed by American physicist Alan Guth. It successfully addresses some of the issues present in the standard Big Bang model, such as the horizon problem and the flatness problem. Inflation also explains why magnetic monopoles, predicted by earlier theories, are not observed. Initial studies of magnetic monopoles led Guth to develop the inflation theory. We'll delve into more details about inflation later. After the brief inflation period, the expansion of space slows down as the energy driving inflation is released. The temperature, which had decreased 10,000-fold, is reheated to the levels before inflation in a process called reheating. During this phase, most fundamental particles are formed, including a plethora of quarks and gluons, creating a plasma-like state throughout the universe. During this time, particles and their antiparticles are continually created and annihilated. However, the numbers of positive and negative particles are roughly balanced until an unknown mechanism slightly favors positive particles. At that point, the excess positive particles form the foundation of today's universe. This also implies that as long as positive and negative particles are not perfectly balanced, there might exist a parallel universe similar to ours but composed predominantly of negative matter. As the universe continues to expand and cool, at around 10 to the power of minus 12 seconds, another phase transition occurs known as symmetry breaking. This transition separates the weak force from the electroweak force, turning it into a short-range force. With this, all four fundamental forces have distinct roles. From this point onward, the speculative elements in the Big Bang theory diminish because particle energies have lowered within the range accessible to high-energy physics experiments. As time progresses, the universe's temperature decreases, allowing more aspects of theory to be tested. For instance, scientists have recreated conditions similar to the quark-gluon plasma era using particle accelerators, validating quark confinement under temperatures as high as 10 trillion degrees Celsius. During this period, quarks cannot bind together due to the strong force. Instead, they form a quark soup. This state persists until 10 to the power of minus 6 seconds. After this point, as the universe continues to expand, the distance between quarks grows. When the separation reaches about 10 to the power of minus 15 meters, the gluons connecting quarks lose their grip, creating two new quarks at the ends of the broken connection. These quarks then pair with the original quarks, forming new quark pairs. As space expands further and the temperature drops to around 10 billion degrees Celsius, the energy isn't sufficient anymore to overcome the strong force. Quarks bond permanently with their neighbors, forming stable hadrons such as protons and neutrons. This process also produces antihadrons, but most of the positive and negative particles annihilate, leaving only a small excess of positive hadrons. At this point, the universe contains protons and neutrons, forming the basic constituents required for atomic nuclei. With the addition of electrons and other leptons, the first generation of atoms is on the horizon.